Good afternoon, everybody. Let's get started. Today, our ninth lecture, the Riemann problem for the Euler equations. So now we are ready to discuss the foundation of finite volume methods for the numerical solution of Euler equations. And first of all, I'd like to remind you once again, very briefly, the main idea. So we are discussing finite volume methods for the solution of hyperbolic equations, or specifically Euler equations of gas dynamics. And the strength of this class of models or methods is that so these methods are based on conservation form of Euler equations, and they mimics the conservation laws of gas dynamics. And this numerical method is conservative. So it means that we can be sure that mass, momentum, and energy equations are valid, are fulfilled on the discrete level. And the application of finite volume method implies that we have control volume or finite volume, and usually it's the computational cell. And our numerical method is written in the form of balances of numerical fluxes through the edges or boundaries of our computational cells. And the question is how to compute this numerical flux. And to do that, we should understand how to solve the Riemann problem for the Euler equations. One more time. So this is a conservation form of Euler equations. U is the conservative variables vector, and F is flux vector. Rho is density, V is velocity, E is total specific energy, epsilon is specific internal energy, and we have a Cauchy problem with the discontinuity in the initial data. So we have UL vector and UR vector, and they correspond. Actually, the idea is that this UL can be UMN and this UR can be UM plus 1n. And if we will know how to solve this problem, we can use the solution in the numerical method. So today I will explain to you how can we use, and so what's the idea, how can we use the solution of this problem in the construction of finite volume numerical method. Some historical remark. So why is it called the Riemann problem? So there's the famous paper by Bernhard Riemann. So he was a German mathematician. Actually, he died just at the age of 40, who made profound contributions to analysis, number theory, and differential geometry. You may know Riemann surfaces from complex analysis, and he is considered by many to be one of the greatest mathematicians of all time. And this is his famous paper published in 1860 in German. And actually it was translated in many languages, and you can see the translation. You can find the translation of this paper into English. There is actually a book, Classic Papers in Shock Compression Science, and you can find the translations of papers by Stokes, Rankin, Hugonio, and many others. Actually, this is very, interesting and useful reading. And actually, even at that time, at 1860, actually he has already introduced many new, not new for that time, new, very important features. He did not consider Euler equations. He considered barotropic media. So he did not consider the energy equation. In this paper, P is a function of rho, of density. Nevertheless, so now the question arises: what will happen if at a given time, at a given position, random discontinuities are present? So actually, he formulated here the problem that we are going to discuss. That is why it is called a Riemann problem. We discussed that the main, items for the structure solution of the Riemann problem. So in the input data of the Riemann problem, there are no parameters with the dimensions of length and time, or time. Therefore, the desired solution is self-similar. So the solution is self-similar if it depends on x and t as of combination psi equals x over t. And today we are going to build this exact solution This is the so-called SOT problem. And the class of self-similar solutions to the Euler equations consists of constant solutions, including those connected through discontinuity, either contact or shock wave, as well as refraction waves. Actually, we discussed the contact waves, shock waves, and the refraction waves. Today, I'd like to remind you the main results for refraction waves and explain the end of the previous lecture a little more detailed. So the important thing is that no more than one shock or refraction wave can propagate in each direction from the discontinuity. So it means that if you have initial discontinuity, for example here, as a result of the solution, we can get only one wave propagating to the right relative to initial discontinuity, and one wave propagating to left. Why is it so? Actually, we can understand that analyzing the waves of the speed of propagation of waves. For example, we proved that the shock wave front propagates relative to the gas ahead of the wave at a supersonic speed, and relative to the gas behind the wave at a subsonic speed. I'd like just to remind you this slide from the lecture about shock wave. So we consider this Hugonian adiabatic curve, and so this red curve is physically relevant curve, and we analyzed the velocity of gas, and we proved that U is V minus D, where V is velocity of gas and D is velocity of shock wave. We proved that U squared 0 over C squared 0 is greater than 1 here, and U squared 1 over C squared 1 is less than 1. So it corresponds to the parameters to the motion of the shock wave relative to the gas in front of the shock wave. So it means that the shock wave propagates at supersonic speed relative to the undisturbed medium, and this means that indicates the subsonic speed relative to the gas behind the wave. So that is why, for example, it's impossible to have two shock waves propagating one after another. So because the velocity of the second shock should be subsonic relative to this media, and at the same time the velocity of the shock wave should be subsonic. It means that sooner or later the second shock wave will overcome the first one. So it means that this configuration cannot be self-similar. So by analyzing the speeds of propagation of waves in Riemann problem solution, it's possible to show, mathematically rigorous, that so only those configurations that we discussed are possible. So one shock to the left, one shock to the right, or one shock to the right, or one refraction wave to the left, and so on. And also it's possible to show that it's impossible to have a refraction wave that follows the shock wave, because in refraction waves, any point of the profile, including the leading and trailing edges, moves at local speed of sound. And for example, consider the case when refraction wave propagates behind the shock wave in the same direction, but the shock wave propagates with the subsonic speed relative to gas behind it, and each point in the refraction wave moves with the local speed of sound. It means that in this case the refraction wave will catch up the leading shock wave, and so on. So by analyzing the speeds of these waves, it's possible to show that it's possible to prove this statement, that no more than one shock or refraction wave can propagate in each direction from the discontinuity. Okay, now we should introduce. So I explained you these pictures, but now we should introduce the indices and variables that we need for further analysis. So index R, subscript R, correspond to parameters that were initially to the right of discontinuity: velocity, density, and pressure. So subscript L correspond to parameters that were for the gas that was initially to the left of discontinuity. And indices C corresponds to parameters to velocity and pressure to the left and to the right of the contact discontinuity. So we discussed on the lecture about the discontinuous solutions that pressure and velocity, they are constant across the contact discontinuity. That is why we should use the same PC here and here, to the left and to the right of contact discontinuity, but we can have, and usually have, different densities, ρ1 and ρ2, across the contact surface or contact discontinuity. It is just the same. And so the idea is as follows. So we have the right wave and we have the left wave, and there is some connection of the parameters in front of the wave and behind the wave, and we have it for right wave and left wave. But pressure and velocities must be the same across the contact discontinuity. So the ideal is as follows. Let's find the parameters behind the shock wave or rarefaction wave from one side and from another side, and then we must say that this pressure should be the same. And on this way, we will obtain the nonlinear algebraical equation for pressure at the contact surface. We will find it, and after that, we will be able to find all other parameters for this for the solution of Riemann problem, namely the speed of the shock wave, velocities, and so on and so forth. So I use the blue line for indicating a rarefaction wave. So on previous lecture, we discussed the self-similar solutions of Euler equations in the form of simple waves. So a simple wave is a special type of law in which two characteristic variables are constant, and the third Riemann invariant propagates along the characteristic line. And it's possible to show, I'll do it now, that inside this rarefaction wave, the characteristic lines are straight lines. So generally speaking, for gas dynamics, the characteristic lines are some curved lines, in contrast to, for example, scalar conservation law. But for the rarefaction wave, for simple wave, the characteristic lines are straight lines. So this is configuration where the shock wave propagates to the left and the rarefaction wave to right, and the configuration with two rarefaction waves. And so one more time. So these terms left, right, they are very relative. So it means that to the left relative to contact surface and to right relative to contact surface, but not in an absolute sense. So it means that all this picture can be rotated and can be in full in the right in this region for x greater than 0. It all depends on the relationship between initial parameters to the left and to the right of discontinuity. Okay, so this is the general structure of the Riemann problem solution. Let's start. So on the lecture dedicated to discontinuous solutions, we have obtained actually all the necessary relationships that are necessary to solve Riemann problem solution. But as I have shown to you at that lecture, we used P and eta. Eta is 1 over ρ. So we use this space by eta to analyze all possible states for gas behind the passing shock wave and so on. But as I explained to you now, we need space PV, because across the contact surface pressure and velocity are constant. And that is why let's rewrite all these relationships that we obtained for shock waves and for rarefaction waves using not P eta, but PV. How can we do that? So I'd like to remind you, so this is the Hugonian adiabatic curve. It's the rectangular hyperbola. So if you have a gas at point 0, under the pressure P0 and some density ρ0, all possible states of this gas, if a shock wave, any shock wave passes through the gas, is defined by this formula. Or we can express quite contrary eta as a function of P if we express eta from this equation. Not a problem. We should specify what does it mean, the left shock wave and right shock wave. The shock wave is considered left if the gas flow through it along the x-axis is directed from left to right. So it means that, for example, if we have this x-axis and shock wave propagates to left, and so for a shock wave, the absolute value of its velocity is greater than velocity of medium behind the shock wave. And but if these values are negative, it means that v is greater than d. Then we introduce the mass velocity or mass flow velocity a sub L as rho times v minus d, and this value will be greater than 0 because v is greater than d. So if for the shock wave a is greater than 0, it means that the shock is a left one, because the gas flow through it along the x-axis, so is directed from left to right. So this is the definition of the left shock wave. Then let's and also let's use the same indices L and C to be closer to this schematic. So, for example, consider this configuration or this configuration. Now, I'd like to use the same indices R, C, L, 1, and 2 in the solution of Riemann problem. That is why we should adapt. We should use the relationships from our lectures to solve Riemann problem. So consider, for example, the left shock wave. It means the parameters in front of the shock wave correspond, so they have indices L, and parameters behind the shock wave C and 1 for density. So it means that we just rewrite our relationships, and now 0 from here comes to L, and parameters with our indexes, they are now parameters behind the shock wave, so parameters at the contact surface C. So this is a relationship for the left shock wave. Okay, but this relationship is written using density and pressure, and we want to use pressure and velocity. So they called PV diagrams, and so the solution of Riemann problem is very convenient to analyze using so-called PV diagrams. For that, let's do the following manipulation. So consider the second Hugoniot jump condition. So this is momentum conservation law across the shock wave. So this is momentum ahead of, in front of the shock wave, and this is momentum behind the shock wave. And let's use this notation. So let's use AL as mass flow velocity. So we can just write the rho 0 v minus d equals a and put it here. Then we can get the expression like this one. And one more time. Again, let's express VL minus d through AL. And then we will get this expression. The connection between, so we try to introduce velocity here. We try to do not use the density or eta. Then we can solve this equation for AL that is obtained the expression for AL, and then take this rho over rho I from this expression here. And now we can express this AL squared from pressures in front of the shock wave and behind the shock wave. Here also, yes, I follow the book of Godunov, who actually, they invented the Godunov method that uses the solution of Riemann problem. And here, within the scope of this consideration, we believe that gas to the left and to the right of this continuity is the same. And so we use just gamma as the specific heat ratio, and we believe this gamma is the same to the left and to the right. But actually, that's not necessary. We can demand that we can use different gases to the left and to the right. And so once again, this formula, it's only some general, in fact, simplest possible consideration. But these formulas can be used for more complex cases when you have different gases, for example, to the left and to the right, or multi-component gases and so on. But so now this is the simplest possible consideration. Okay, so we expressed A as a function of pressures, and then we can take this expression for momentum conservation law and put this A here, and now we obtained this simple formula actually written for the shock wave, but in terms of pressure and velocity. So all possible. So if you have a shock wave, the relationship between the pressure and velocity behind the shock wave with those in front of the shock waves for the left shock wave, so they can be found from this expression. So we can consider just in the similar manner the right shock wave, and we can obtain the relationship for pressure and velocity for the right shock wave. Actually, all these expressions we obtained previously, but it's just some arithmetic, some manipulations with formulas, and I explained to you how to write the formulas for the shock wave, not in terms of pressure and density, but in terms of pressure and velocity. One more time, because we try to obtain the relationship through the so for the parameters through the contact discontinuity. And velocity and pressure are constant through the contact discontinuity. That is why we try to use this pressure and velocity notation. We analyze the shock waves. Now we should get the same expressions for refraction waves. The previous lecture was about characteristic analysis of the Euler equations. So now we know a lot of different forms for Euler equations. So the most physically relevant and suitable for numerical implementation for finite volume methods is conservation form of Euler equations, because it's written in the form of conservation laws. In the previous lecture, I showed to you how to get this form of the Euler equations in primitive variables. How can we transfer this one to this one? And this form is more suitable for theoretical analysis because it's much more simple in comparison with this one. So the structure of Jacobian matrix is is simple. We have a lot of zeros here. It is written for as well as here for ideal gas equation of state. And we carried out characteristic analysis of the system. So we took this matrix A and we computed the eigenvalues of this matrix A, eigenvectors of this matrix A, and computed the matrix composed of right eigenvectors and left eigenvectors of matrix A. And we have shown that it's possible to write the characteristic form of the Euler equations. So we introduced the characteristics of the Euler equations. And the third form, that is for smooth solutions, they all are equivalent. So we can write that Euler equations can be written in the following form. There are three Riemann invariants, V sub 0, V plus, and V minus, and dV sub 0 equals 0 along the characteristics dx equals V dt. It means that this invariant propagates along the characteristic curve dx equals V dt, and this wave is called entropy wave. And we have shown that so this expression can be integrated analytically. It corresponds to ds equals 0, where s is entropy. That is why it's called entropy wave. And there are also C plus and C minus characteristics, and corresponding waves are called acoustic waves. And along these characteristics, V plus and V minus invariants propagate. So once again, this one, and this one, and this one, they're all the same Euler equations, but they are suitable for different things. This one for numerical implementation for finite volume methods, this one for theoretical analysis, but also a number of numerical methods also rely on this form of notation. For example, some reconstruction procedures. characteristic form is very suitable for implementing boundary conditions. Because if we want to use so-called non-reflecting boundary conditions, subsonic boundary conditions, we should analyze the disturbances that propagates not in form of some pressure waves and so on. So disturbances in gas dynamics in Euler equations, they propagate along these characteristics. That is why if you want to analyze and to stop propagating inlet of some disturbances into our computational domain, we should carefully work with these relationships. So everything depends on your problems, and you should just know that you can write the same system using totally different notations. So I think it's so if you do not know that all these things are just for Euler equations, it can be a bit confusing. If you, for example, read some paper and you can think, so what does it mean? But they are just Euler equations. And after that, we said, okay, we would like to find self-similar solutions of this system of equations. And we carried out the typical decomposition, diagonalization of matrix A as the product of omega L, lambda, omega R, put it in our equations, but due to non-linearity, we obtained only compatibility conditions along characteristics, and that's it. So this is again another form of Euler equations. But after that we said, okay, let's say that now Wk, where W is a vector of primitive variables, it should be self-similar solution. It means that dwk over dx equals to this one, and dwdk over dt equals to this is equal to this one, and we put them in compatibility conditions along characteristics and obtain this system that can be written in the component-wise form like this one, and said that the exact solution, the exact self-similar solution must satisfy one of the following three system of equations. So either this 1 lambda 1 minus c equals 0 and expressions in two parentheses equals 0, or lambda 2 equals xi and expressions in parentheses here and here equals 0, or the third option. And that's it, because they are all together should equal 0. And as an example, we consider this one, second case. Lambda 2 minus psi equals 0, a equals 0, and c equals 0. And we have shown that actually they're not just some mysterious formulas that connects pressures, densities, and so on. We have shown that the second condition, namely a equals 0, is just the same as the relationship for isentropic process. So if you consider p over rho to gamma equals constant and take the derivative, it turns out that we will get just the same relationship as a equals 0. So it means that the self-similar solutions of Euler equations are isentropic flows. And also we have the third expression. So it should equal 0. And after arithmetics, that is not so important. So it's possible to show that this condition, the third equation, is equivalent to v plus 2c over gamma minus 1 over psi. The derivative of this value with respect to psi equals 0. And this is just the same as v plus. For isentropic flow, ds equals 0. So this v plus Riemann invariant is 2c over gamma minus 1. So we obtained that in a simple way. Entropy is constant, v plus is constant, and v minus is constant along the characteristic dx equals v minus c dt, because it's always true. So we obtained, and we started the previous lecture, as you can remember, we analyzed we considered a linear system of hyperbolic equations, and I introduced the simple waves. So a simple wave is a solution, is a type of flow in which only one characteristic variable is not 0, like in here. So we obtained that in this flow, two characteristic variables are constant, s and v plus, and one is not constant. But what does it mean that? So it's not constant everywhere, but it constant along the characteristic curve. But what does it mean? It means that along this characteristic curve, dx equals v minus c dt, all characteristic variables are constant. They remain constant along this characteristic. So to the end of the lecture, I will show you the just examples of all these theoretical statements, and I hope that you will realize. So what does it mean? But we should get the necessary theoretical results from here. Thus, in general, all variables remain constant along their characteristic dx equals v minus c dt. So in this type of flow, all variables remain constant along the characteristic curve. This characteristic curve, in this case, because we have chosen this lambda 2 equals psi, dx equals v minus c dt. So the characteristic is a straight line, because all the variables are constant along this characteristic curve. So that is why in simple waves, the characteristics are straight lines. And that is why when people write these diagrams, they call this refraction wave refraction fan, like fan that you use when the weather is hot. It's not just the schematic, because indeed here in this refraction wave, all characteristics are straight lines. So once again, generally speaking, that's not true for gas dynamics, in contrast to scalar conservation laws. But in this type of flow, they are straight lines. And actually, we have shown it, strictly that actually, yes, they are strict lines. Actually, during this consideration, we did not. Why do we call these waves refraction waves? Why not compression waves? So actually, the thing is that in refraction waves, the characteristics expand, and they will not intersect. And for compression waves, the characteristics, will intersect sooner or later, and actually very soon. And so the compression wave can be also a self-similar solution of the Euler equations, but for a very, very short time period. And after that, they will, meet each other with the formation of a shock wave, as we discussed for scalar conservation law. That is why, in fact, the solution that we obtained, simple waves, self-similar solutions, they are only refraction waves. That's also we should take into account. And finally, a simple centered refraction wave is a refraction wave in which all characteristics originate from a single point in the xt plane. So suppose we want to know the solution of this Riemann problem. Everything starts here at 0. So this blue structure is called a simple centered refraction wave. It's a simple because inside this wave we have these relationships. It is centered because all the characteristics starts at 0, and a refraction because it couldn't be compression wave, because these characteristic lines will intersect. And again, so we can introduce the definition of left refraction wave and right refraction wave. For the left refraction wave, rho v minus psi is greater than 0, and v minus psi here for this, for example, structure is c, speed of sound, is greater than 0. It means that this refraction wave is left refraction wave indeed. So we need these conditions, and we need to understand them, and I will show how will they implement in the final solution of the Riemann problem. Okay, and actually this is the reminder of previous lecture. I think the previous one was the most difficult lecture, because it's really very difficult to understand all these nonlinear waves for the Euler equations. But nevertheless, these are these two expressions. So S equals constant V plus equals constant V minus is constant along the characteristics curve, and we can write it here, these expressions. And so once again, consider, for example, this left refraction wave. How can we get expressions in terms of velocity and pressure? Consider, for example, this expression. So inside this reflection fan, the entropy is constant. It means that we can take the bounding characteristic lines, for example, this one, and write that entropy, or so this p over rho to gamma for this characteristic line is the same as for this characteristic line. But for this, so it can be expressed through rho1 and pc. And for this characteristic line, we use rho L and PL. We know them. So this is the first expression, and we should do the same thing for V plus invariant. It should be the same for this characteristic line and for this characteristic line, and we use it, and we get this speed of sounds, and the ratio of this speed of sounds can be expressed using the pressures or densities, and we can use this expression for densities, and actually finally we get the relationship between velocity and pressure. So once again, we would like to get the expressions for the shock wave and for refraction wave using only velocity and pressure. And then we will say that pressures here are the same, and this is the way how we're going to solve the Riemann problem. You can find this expression in many books about computational gas dynamics, but once again, here I'd like to show you how can you get them. So for me, it's the most accurate and understandable way. Not just write them down with the words that it's obvious. That's not obvious, but it's possible to get on the way of construction self-similar solutions of the Euler equations. So what's the result? We know that our waves in the Riemann problem solution, each wave that propagates to the left and to the right should be either a shock wave or a reflection wave. So we obtained expressions for left shock wave and right shock wave, and for left refraction wave and for right refraction wave. Now we have all the ingredients in hands to build the Riemann problem solution. How to do that? I'd like to show it on an example because it's much more useful, and in contrast to general consideration with no connection to any physical problem. I'd like to show you how to solve Riemann problem on the example of the well-known SOT shock tube or SOT test. What does it mean, SOT? So it's another famous paper. SOT is a surname. Gary SOT is a researcher who published a paper in Journal of Computational Physics, GCP, in 1978, a survey of several finite difference methods for systems on nonlinear hyperbolic conservation laws. So that's again the role of a person in history. In this paper, he just analyzed and compared a number of numerical methods, and he just chose the specific Riemann problem for that. So in this study, in the above numerical methods, the following test problem was considered. Density to the left 0, pressure 0, velocity, so 1, 1, and 0. And to the right, density 1/8, pressure 0.1, and velocity 0. Just so imagine this. So he just suggested these parameters, they do not correspond to anything. And they are all dimensionless. So do not think that it's in pascals or in kilograms or meters. No, it's just dimensionless. So, for example, if you have atmosphere, you can choose some scaling, like say that your pressures will be in atmospheres, and then you can divide 10 to the 5th power, and you will get just unity. So just dimensionless parameters, and so this is, you can imagine it. So this is parameters to the left, parameters to the right, and this is the exact solution. So we're going to obtain this solution. And he considered different numerical methods. For example, this is the Goodenough method, and compared how the different numerical methods can resolve shock wave and contact surface refraction wave. And after that, many people, and till now, if you try to publish a paper and introduce some numerical method, so this maybe the first or the second verification or validation test should be the solution of this SOT shock tube problem. Actually, this is a mild test, so the gaps in the pressure are not huge, so just 10 times. So that's not very demanding test case for the numerical method. But anyway, Why is it called short shock tube test? Because, as I already mentioned, the closest analog to physical interpretation to the Riemann problem, if you take into account shock physics, is a shock tube. So it's just some PhD thesis of some guy, I don't know, but the picture is very beautiful. So the shock tube is just a tube with a high pressure chamber and low pressure chamber, and the diaphragm, and suppose that this diaphragm is ruptured, and there is some flow towards this wall, and it will have the form of a shock wave, and behind the shock wave we have a pressure rise. So this green color corresponds to low values, and here usually the blue color is low values, but nevertheless, so some high values, some low values. Behind the shock wave we will have some pressure rise, and here you can see some gradient in color. It's the propagation of a refraction wave, and after that the shock wave. So before the moment when this shock wave reaches the closed end, the solution will be self-similar. And after the reflection, no, but this is just illustration why do we need shock waves. So when the shock wave reflects from this end wall, you will get much more high pressure in comparison with the pressure behind the shock wave. And for example, if you have chemically reactive media here, you can study, for example, the induction time before the mixture will explode and so on. So this is a very useful apparatus for a lot of research. And also, actually, you should also understand that I explained to you just one-dimensional behavior of this media. But actually, in reality, in shock tube, so it's 2D or actually a 3D problem, we will have a boundary layers that will develop behind the shock wave, and after the shock wave will reflect from this end wall, they will interact with these boundary layers and so on. So that's to the question of the errors of the numerical of mathematical model. So you can consider the same problem on different levels and use different mathematical models. So you can consider this problem in 1D, in 2D, in 3D, using Euler equations, Navier-Stokes equations, and so on. And but now we consider it just for an example of a Riemann problem for 1D for Euler equations. So PV diagram. So what does it mean? It means that consider the so this space, the x-axis correspond to velocity of gas, and y-axis ordinate corresponds to pressure of gas. So in short shock tube problem, parameters to the left are as follows: pressure 1, velocity 0, density 1, specific heat ratio or diabatic index 1.4. You have lower pressure and density to the right, and the same gas here. Let's put this point E. This point E corresponds to initial state of gas to the left. So because the velocity is 0, it is on this y-axis, and the pressure corresponds to 1.0, right? Yeah, so it's here. Oh no, it's the right state. It's the right state. So point E corresponds to the right state. So it means that pressure is 0.1 and velocity is 0. And this point B corresponds to the left state. And so the pressure here is 1, but velocity is still 0. That is why it's also on the ordinate axis. What should we do? So we obtained these 4 formulas. This is for the left shock wave, for right shock wave, for left refraction wave, for right refraction wave. For gas to the right of discontinuity, we should plot curves corresponding to all possible states. So we can transfer this gas, we can compress it in shock wave, or the pressure can be decreased in a refraction wave. So for the state E, to the right of initial discontinuity, we should plot Hugonian adiabatic curve. So is the right shock wave here, V equals VR, and so on. This is the right shock wave. So I just use this expression, And this is not a schematic, so indeed, if you take gamma equals 1.4 and these parameters, so the PV diagram for the shock tube problem will look like this one. And you also can plot Poisson adiabatic curve, or it means the right rarefaction wave, this one. We know actually, we discussed it when we discussed the Rankin-Hugoniot jump conditions, that Poisson adiabatic curve and Hugoniot adiabatic curve, they very smooth couples, so the first and the second derivatives of these curves at this point are the same. And in this sense, we can just plot it and forget about colors and consider this blue plot and this red red curve as just one, one black, very smooth curve, and it corresponds to all possible states for this gas in this problem. And we can do the same thing for this gas. We can plot Hugoniot adiabatic curve and Poisson adiabatic curve. And again, so they're very smooth couples, and you can forget about color, and this will be just one black, for example, curve corresponding to all possible states for this gas. And the solution, the parameters at the contact surface, will be on the intersection between this DEF curve for right gas, gas to the right of discontinuity, and ABC curve for left gas. You can see it will be some point S. And the coordinates of this point S will be about 0.93. We can, remember this value, and the pressure will be about 0.3. And actually, this is a solution, but what does it mean, solution? It's VC and PC, velocity at the contact discontinuity and pressure at the contact discontinuity. So this is the first main result in consideration of this picture. And the second result is that now we can understand the structure of the solution, because the point of intersection is on the red curve for right gas, EF. It means that the shock wave will propagate to the right, and this S curve is on the blue part for the left gas. It means that the reflection wave will propagate to left. And actually, this PV diagram can explain to you the parameters at the contact surface, and also explain to you which configuration among possible states, these possible states, will be implemented. So from consideration using PV diagram, we can find these PC and VC, and understand that in such shock tube problem, you will get this configuration. The shock wave will propagate to right, and the reflection wave to left. Okay, I think, okay, we still have some time. How can we find these values, PC and VC? So the problem is that it's not possible to find analytically. Actually, it's not very difficult, but these curves are defined not using some differential or integrals and so on. They're just some algebraic formulas, but with the roots, powers and so on. It should be defined numerically. So from a mathematical point of view, we should solve nonlinear algebraical equation, because we have two curves that can be that must be intersected, and we need to find the coordinate of this point S. Different numerical methods for that can be used. It's topic of some basic course on numerical methods or calculus or something like that. We should just find the root of nonlinear equation. But here so we can express that. Let's find VC from here. Let's rewrite these expressions and express VC here, 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 and here, and say that this VC should be the same. And for example, this VC is VL minus this guy. Let's denote it as F. of Vc is equal to Vr plus this guy. That is why, so we introduce this function f in such a manner. So once again, it's just we just rewritten these expressions for left and right refraction waves or shock waves, and then say that this say that velocities at the contact surface should be the same. So if pressure is greater than pressure to the left and or to the right, then we have shock wave. Otherwise, we have a refraction wave. And we can suggest to use the Newton iterations to solve this equation. For that, we should put these VL and VR to left and use the standard common formula of Newton method. For that, we should know the derivatives of this function f, and the important issue, we should have some reasonable initial approximation. So you may know that for numerical solution of nonlinear equations, the initial approximation is of great importance. But here, actually, the solution of the Riemann problem is, very massive. It's the procedure. If your numerical method is based on the solution of Riemann problem, it means that you must effectively solve this problem many times inside your software. And that is why actually people have already developed very efficient numerical methods how to find the intersection of this adiabatic curve. And so I just explained to you this effective numerical method. So in fact, the Newton method with reasonable initial approximation can provide you the solution. I will show the good initial approximations later. Okay, I think we should have a break, and after that I will explain you the solution of the short problem. Okay. I explained to you how to find the pressure and velocity through at the contact surface. So they are the same to the left and to the right of the contact surface. But actually there are a lot of other parameters that define the structure of our solution. So first of all, once again, we understood that the solution would look like a shock wave propagating to the right and the refraction wave propagating to the left. And we can find with actually, yes, it will be found using some numerical method, but you can find these values with any necessary accuracy of the numerical method. So the accuracy that you need. But anyway, you should use iterations, and that's why this numerical. So the numerical method that will use the solution of the Riemann problem is not very economical. So it means that that is why people thought and developed a lot of other numerical methods, and they try to develop numerical methods that would be actually also accurate and resolve all the necessary structures, but without iterations. And so next time we will discuss the HLL and HLLC numerical methods as approximate Riemann solvers, because Gordon method is great, but it's not very cheap. And also, although it's based on the exact solution of the Riemann problem, it still has a number of features and disadvantages. So it does not mean that this method is the best one, actually. Anyway, so we know parameters at this contact surface. What can we do? Let's consider this refraction wave. So this part is called a refraction wave. It had a head of the refraction wave, this point, and a tail of the refraction wave. We know that this is a simple wave, and inside the simple wave, V minus C equals psi. V minus C equals psi. ds over the psi equals 0. And this guy is equivalent to V plus over psi equals 0. Now, so I told to you that I hope that you will understand the meaning of this, of all these things, and now we can apply them directly and show what does it mean. So consider any point A inside this refraction wave, for example, point A here. For this point, velocity of this point minus speed of sound at this point is equal to xa over t, where xa is the coordinate of this point and t is time instant. For this point, Va plus 2Ca over gamma minus 1, so this complex is constant in this wave. It means that it is equal to this complex for the head of the refraction wave. So we should take just VL plus 2CL over gamma minus 1. But we know this VL and CL. Actually, we have two equations for two unknowns. We do not know VA and CA, but we know parameters with L subscript, and we know the coordinate and time instant. So we want to find velocity and speed of sound at specific point at specific time. We can solve them and find VA and CA. If we know VA and CA, we know that the flow is isentropic, and that is why we can find the pressure and density, actually, from these two expressions. Actually, from here we can find PA, and from here we can find rho A. And that's it. So the refraction wave is defined. This density is equal to density at this point, and the density of this point can be found from expressions for refraction wave. This is for left part of our solution to the left of contact surface. So once again, initially this continuity was here, and we had a gas from left and to the left and to the right. Then this contact surface corresponds to this initial boundary. It moves. So we have the motion of this boundary, and still this is the gas that was initially to the left, and this is the gas that was initially to the right. And additional to the motion of this contact surface, we have disturbances that propagate in this gas. So that is why, once again, so you can keep in mind this interpretation. So we have the motion of your media and additionally motion of disturbances in this media. So that's all about the same. That's all about the same things. So we have the motion of media and propagation of disturbances in this media as well. So consider now the shock wave. So we know the pressure and velocity here. If we know pressure and velocity here, we can compute this AR value. So actually we have all the necessary things. For example, here, if we know PC and we know parameters, initial parameters to the right of this continuity, we can compute this AR. If we can compute this AR, we know that AR is rho R d minus VR. We can find d from here. D is the velocity of the shock wave. We know parameters in front of the shock wave, we know the speed of the shock wave, we can find the density behind the shock wave, and that's it. So the message is that if we know the parameters at the contact surface, we can find everything else. So the problem is solved. So this is the structure of the density, and this is the structure of, this is the solution for velocity, typical velocity. We can see that the profile of velocity in the refraction wave is linear. It is so because you can check for the specific time instant, you can find the velocity as function of x, it will be a linear function. So this is the typical behavior of velocity in the simple wave, in the refraction wave. And in contrast to density, you can see there is no gap in velocity. And you can check this value. It's about 0.93. It's just the same as here. So we have found the velocity of the contact surface, and this velocity is just the same as velocity of media itself. So the contact surface and the gas itself, they both move with the same velocity. That is why it's a contact. That's why it's a contact surface. Shock wave or reflection wave. So you can see that profiles for pressure, for density, for velocity, they're all different, and the last one is for pressure. And again, we don't see any gap at the contact surface, which is somewhere here, and the contact pressure is about 0.3. It was also obtained using a PV diagram, and that's it. So we constructed the exact solution of the Riemann problem on the example of the third shock tube problem. I constructed these profiles using the program for the construction of the exact solution of Riemann problem. And additional details will be clear for you after explanation of how does this program work. So I'd like to show you the details of the program which compute these profiles of the exact solution of Riemann problem. And I also will share this program, and so if you need, you can use it. And so the second part of the lecture is how can we implement and compute this, and it will also explain a lot of things, because maybe you think that you understand all these theories, but when you try to implement it in code, it turns out that many things, so you still don't understand a lot of things. So now I'd like to explain to you the program for the construction of the exact solution of the Riemann problem for the Euler equations. So I used it as for program for ordinary differential equations, C++. I don't use different this ideology with classes and so on, because all these computational things, the procedural approach works well for that, and it's a project for Visual Studio. And there is a main CC file where we have main loop of the special coordinate. All constants are here in main H. Actually, we have a grid, so we have not to get the numerical solution, but we want to get the exact solution at specific points of our grid. So it's a set of restriction of our exact solution on a grid. It's very convenient because usually it's necessary to compare the numerical solution with the exact one, and so we can get the exact solution also on some numerical grid. Godunov CC, so it's file with functions for calculating pressure and velocity and at contact discontinuity, and all the necessary function to compute the structure of the Riemann problem solution. So I have file with different functions specific to Euler equations, such as computation of speed of sound and so on, and some additional working files. So as a result, the program computes special distributions of density, velocity, and pressure at specified moment in time. So just the profiles I have shown to you. So we should find some time instant, for example, 0 to 0.2, once again, not seconds or microseconds, some dimensionless time. And this is the solution for this time. And we didn't discuss the boundaries, right? So usually we have some boundaries. So the solution remains self-similar up to the moments when the disturbances reach these boundaries. So you should always keep in mind what the problem do you solve. So it's not good that, if you don't understand how does it work, you can take, for example, t equals 10 or 12 or 20. And you can run the program and you will see a strange result, because at that time, so all these waves, they come through the boundaries and you will see some constant or I don't know what, or some linear profile, so whatever. Because you should understand that what the problem do you solve. So, okay. This program has input file where you can specify the necessary parameters. Suppose we want to compute our exact solution of the computational mesh on a mesh with 1000 cells, and we need to choose the interval. Suppose it will be minus 0.5, 0.5, right? At this interval, we would like to build our our exact solution. So this pattern corresponds to the solution of third shock tube problem, and we did not mention any boundaries, but now we have. So suppose we have boundary minus 0.5, 0.5. we want to get the solution at the time instant 0.2. So it means that we should write this horizontal curve t equals 0.2 and say that we want to get solution for this time instant. It means that the parameters should be undisturbed. After that, we have the parameters behind the shock wave. After here, we have parameters behind the contact discontinuity. Here, we have the parameters inside the refraction wave, and here are disturbed parameters to the left of discontinuity. So I just described to you. So here, right? The motion along x-axis undisturbed parameters behind the shock wave, behind the contact discontinuity in the refraction wave, and to the left of initial discontinuity. First of all, I build computational mesh. It's uniform. Then we need to compute pressure and velocity at the contact surface. Actually, I explained to you how to do that using PV diagram. And then the idea is as follows. So there is a loop over the cells, and in this loop, we analyze the behavior of this ray, which starts from 0. So it starts from 0 and moves from this position to this one. And for each ray, we define the area in which it situated. So S is x over t. So it's our self-similar variable. And for this ray, there is a function called sample sample solution. So it's the sampling. It means that we should define in which region we are, and just write the result. So in this file, we can specify left parameters, parameters to the left of initial discontinuity, parameters to right. Okay, this is the main loop general structure. And now we should consider the function calc contact pressure, velocity, and sample solution. How can we find parameters at the contact surface, and how can we sample the solution? So as I told you, we do not use so the PV diagram is not used directly. Instead of this nonlinear equation is solved. So the calc contact pressure velocity function looks like as follows. So first of all, there is also an important feature to discuss. The Riemann problem not always has a solution. Why is it so? Because it corresponds to motion of gas, and so it's we can imagine some situation where we try to use some external parameters. For example, consider that we at initial time instant provide speed of gas several kilometers to the left, and for example several kilometers per second in the opposite direction. It's not possible for the gas to provide such type of flow. From a mathematical point of view, this so-called case of vacuum formation. So if this condition is not valid, it means that there is no dissolution of Riemann problem. And that's also a very important thing, that especially if you, for example, use some softwares as a black box, a typical one of the most important requirements to the engineering software is that it should provide you an answer in any way. Even though if you have some bad initial conditions or the solution does not exist, so an engineer wants to get an answer, right? And I don't think that it's a good decision, because in this case, you should understand why do you have this situation. Why somebody provided you with parameters when this problem does not have a solution, and that's the most important thing. Maybe you should use another model or another error and so on. It's not good to do some cutting. So if something doesn't work in program, you can have cutting and cut some bad parts of your solution. Anyway, we should check if the solution exists. It also can be seen using this PV diagram, So these curves cannot have intersection, at least for positive pressures. The next question, we need to choose the initial guess. So it's very important because we are solving the nonlinear equation. After we have chosen initial guess, we do these Newton iterations. Calc f and df computes this f function and the derivatives of f with respect to p. And you can see that it's very easy to follow the code because I try to code just as, for the code to be very similar to formulas. And that's it. And you do these iterations until you reach the necessary criteria, the necessary accuracy. And after you find the pressure at the contact surface, you can find also the velocity of contact surface. So now we can discuss how can we choose the initial guess, and how can we choose the initial guess. It's also very meaningful discussion. How can we choose it? There are different approaches. How can we do that? For example, yes, and so all this code actually was taken from book of Torah. It's provided in Fortran, so I use C, and actually this code is very good, and I use in my scientific research as well. And different people use different strategies how to find the initial condition. For example, Godunov, in his book, used the simplified sonic discontinuity to get the initial guess for the iteration, for Newton iterations, to find the pressure and velocity at the contact surface. Torah provides the following idea. He also computes some guess from linearized problem. Actually, this formula comes from consideration of acoustic systems. And then he introduced some empirical parameters equals P max ratio. So he analyzed. So there is no unique, procedure how to do that. As for any nonlinear equations that you would like to solve, and he analyzed if the initial gap in pressures to the left and to the right, if it's too big, he used the analytics for so-called two rarefaction waves or two shock waves. If the initial gap is small enough, the linear approximation can be used for initial guess. But what does it mean, initial guess for two rarefaction waves or two shock waves? It turns out that, so the problem, why do we need iterations, is only because it's possible to have intersection of red curve and blue one. It turns out that if two blue curves would intersect, and it's possible. For example, you can imagine that this E point, for example, here, and then the red curve will go here, and the blue here, and you will get the intersection of two blue curves. So it turns out that if you have intersection of two blue curves or two red curves, the solution at point C will found analytically. And this analytical solution can be used for initial guess of few iterations, for your iterations. So if we suggest that we have intersection of two blue curves, it means that we have solution with two rarefaction waves. And PC can be found from this equation analytically. We can just denote PC 2 gamma minus 1 over 2 gamma as some variable and just express it from here. And if you consider intersection of two red curves, it corresponds to initial guess based on two shock waves. And in this case also you can find the solution analytically. And Toro suggests to use the initial guess based on two rarefaction waves is the linear approximation as less than minimal between two initial pressures. So for the case of third test, we have PL equals 1 and PR equals 0.1, and the P linear is just in between, so it's the average value between them. And so this coefficient was chosen equals to 2.0. And so this linear is, but the real ratio is 10, right? The real ratio. And this linear approximation, the initial guess based on linearized problem, 0.55 is greater than 0.1. That is why this part of code, initial guess based on two shock waves, works, and this function will return 0.31526. And you can remember that the real pressure is about 0.3. So actually this solution is already very close to the real one. So actually, if you choose relevant initial condition, the iterations will converge very fast. So you need just 2 or maybe 3 iterations to get very good approximation for your parameters at the contact surface, PC and VC. Actually, you can suggest not only Newton iterations but simple iterations. Different options are possible. Yeah. This is the function to compute f and df. So in this function calc f and df, we compute really f and df. So for example, for refraction waves, and again, I suggest you to keep, so you will always meet the problem. You should keep the balance between the efficiency of your code and way more clear way of how can you write it. And if you do academic research, I can suggest you to pay more attention to the readability of your code, because you should work with that. Your students should work with that, and you should will work. And you should, if you will write very efficient, fast code, but if nobody will be able to read it, that's very bad. That is why. And if you want to have a program that will, live without you. You should have a lot of commands and document with very detailed description of what's going on, and so it's better to have just the same formulas right in code which will correspond to a document, because I have an experience in working with old Fortran codes, and these codes were written in such a manner that even authors were unable to understand and explain anything in this code, and that's very bad. So here we have a code for f corresponding to a reflection wave, this one, and this part corresponding to f for shock wave, this one, and we can actually accurately compute derivatives here, and so that's it. The most maybe difficult function, but one of the most important, is the function of sampling. So okay, we computed the PC and VC, but now we should collect the whole solution. How can we do that? In cycle, right, we consider all rays which starts at this point 0. Actually, it will start from this end. We analyze. So if this ray to the left or to the right relative to contact surface, initially it's here. So it's to the left side of the contact discontinuity. Okay. Then we should check, is it here or here or here? Is it to the left of the refraction wave, or inside the refraction wave, or between the refraction wave and contact discontinuity? If it's, and yes, and we can compute the SHL is the speed of head of refraction wave, and STL is the speed of tail of refraction wave, and they also can be computed. And so we contact here is 0.9274, and the velocity of this head of refraction wave and tail of refraction waves are these values. You can see it's very close to 0, but it's only for this test. And this is the schematic, and this is the real picture. How will it look like for the SOT problem? So it's the propagation. So it's a characteristic corresponding to a shock wave, contact wave, and a refraction wave. And you see here, so it's almost near to to 0, but actually it may be, so the location of characteristic can be here, so it's just in this test case. There is no deep sense in that. But you can see that the tail of a reflection wave propagates so in such a manner that it's almost 0. So it means that, for example, if you look at profiles, for example here, right? So 0.5 is the initial position of discontinuity, and you can see that this point corresponding to tail moves very slowly, so it's almost at the same point. So again, it may be a little bit confusing, especially when you compute this solution numerically. You can think that maybe this point should be at rest, should be here, but no, it's just for this case. So this refraction wave should move, and so just for these parameters, it moves in such a manner that tail, so the velocity of tail is very low. So okay, so we start here. First of all, we are here, and we take parameters on the left side of this continuity. Okay, then we here inside the shock wave. If we're inside the shock wave, we take parameters here. Then we here between the refraction wave and contact discontinuity, and so on and so forth. So actually, if you have this diagram and look at on it, everything is very clear actually. So we have all the necessary formulas from from consideration of the Riemann problem, and you should just carefully analyze all cases. But also a very important thing to discuss is that this is for Euler equations. So this was done for many years ago, and at the same time there are a lot of other hyperbolic models. And generally speaking, it's possible to construct the solution of Riemann problems for more complex systems, but you can imagine how difficult it can be. So you should analyze the whole wave structure for the problem. And for Euler equations, even here it can be not very easy, right? But for much more complex system with more number of variables, with more number of waves, you can have much more difficult procedure how to build the Riemann problem. That is why for a number of hyperbolic models, still, so you may meet even now papers on the development of Godunov method and Riemann problem solution of some problem. Why is it so? Because that was not so easy to do, and only now people, can construct the solution of the Riemann problem that can be used later to for the numerical solution to implement the Godunov method. Actually, the numerical method based on such consideration, I think it's the most difficult from an implementation point of view, right? Yeah, I understand that. And next time, I will show you how this actually very simple, in a simple manner. This method can be used in construction of the numerical method. Why? Because this sampling finishes with these 3 lines: formation of the output vector with the result. So for each array S, you understand where we are, and we take density, velocity, and pressure corresponding to the exact solution. Once again, we started with what? We started with this picture. So we need to compute numerical flux, and this H, right, corresponds to, if we do not have moving boundaries, moving grids, and so on. So the H corresponds to x equals 0 in our consideration, or x equals to location of initial discontinuity. And now we know how to build the exact solution. So this x equals 0 correspond to the H of our computational cell, and we only need to understand in which part and take parameters corresponding to the necessary part. For example, in this picture, the axis x equals 0 correspond to area between the contact discontinuity and refraction wave. It means that these parameters ρ1, Vc, Pc should be taken. We should take them and put into the flux. Rho, ρv, ρe, and that's it. And that's the essence of Godunov method. So we should solve the Riemann problem. Or, for example, if the configuration would be so that the contact discontinuity will be here, then we would take ρ2, Vc, Pc, and so on. So depending on the solution of the Riemann problem, we should take the necessary density, velocity, and pressure and just put it into the flux and use this flux in the numerical scheme. And that's so the idea of the Godunov method. And once again, that's great. It's very physically relevant, but to find these values, you should do iterations. You should do write this code. And so this is 1D. In 2D, it will be difficult. In 3D, it will be also much more difficult. I will show you. We will have a lecture about the finite volume method in 3D. And actually, there is strong similarity between 1D and 3D for sure. But anyway, in multi dimensions, you should. So the procedure will be much more difficult. So that is why I'd like to explain you the next lecture, right? The connection of this lecture with the next one. So that's why people would like to use more, they would like to use simpler numerical fluxes to keep the accuracy of Godunov method, but at the same time, it should be simpler to implementation and cheaper in terms of computational costs. So there are different approaches how to do that. Next time we will discuss one of them actually, HLL method and HLC method. Oh, okay.